Welcome, thank you for coming to the CAM Colloquium. I'm very honored and pleased to introduce Anima Anandkumar from UC Irvine EECS department. Anima graduated with a PhD from ECE here at Cornell in 2009, and since then has really been making a name for herself in the world of statistics, machine learning, and related topics. She's won the Army or Air Force Young Investigator Awards, the Microsoft New Faculty Fellowship. Her papers have appeared in Annals of Statistics and all of the top machine learning conferences, and Anima is one of those people who every time I have a conversation with her, I learn something new and really interesting to me, and most importantly, something that I feel I can use somewhere in my future. And so I hope you will give her your full attention, and hopefully all of you will have the same experience I always have listening to her.
Thanks a lot, Bobby, and it's, as always, it's just a pleasure to be back here. I just feel like, after this talk, I'm just going to go back to my office and be with the other grad students. It was just such a wonderful time of my life, and it's really good to relive that now. And so today I'll be talking about the work. I've been looking at these tensor-based approaches for, I would say, about a year now. And in a broad sense, I'm interested in learning latent variable models. So now with all the advent of big data, we have lots of data available, so we want to look at approaches that can model them in a scalable manner. By that I mean, you can think of these data sets as being high dimensional. Typically there are lots and lots of different variables that you want to ask how they relate to one another, and it's always pertinent to think of latent effects. You don't observe all the effects, there are always some latent variables that you want to incorporate. And the first question is, what are some reasonable ways to account for these hidden effects? I come from a probabilistic background, so having probabilistic modeling for latent variables is natural to me, and I've been interested in graphical models for a while now, so thinking about graphs to model relationships between the variables, and in particular thinking of them as conditional independence relationships is very powerful. So this started out more in the AI community and is now very relevant to machine learning of very large data sets. So I've been interested in graphical models in general, and in particular with these latent variable models, I've been interested in asking how conditional independence relationships lead to tractable forms. In particular, asking how, if I want to think of moments from this distribution, does this conditional independence relationship buy me? What does it buy me, right? How does it make the problem more tractable? And how I can, and now there are two aspects of the question. First of all, how, say, observing the moments of the distribution, how can I identify the parameters? So that's the learning question. I'd like to learn about these latent variables. I'd like to learn how these latent variables relate to the observed effects. So that's the first question of how, if I had access to moments from the distribution, how can I do this learning? Is there identifiability if I told you the exact moments? And the other is algorithmic. What are some computationally tractable means of obtaining the parameters from these moment forms? Right, so this is kind of the overall picture, and here I'd like to focus on a very particular class of latent variable models, which are the community models. So these are relevant in a number of different areas, especially in the area of social networks, biological networks. So many times we have pairwise or higher order relationships between, say, nodes in the network, and I'd like to then ask about the groups or communities that the nodes belong to based on these relationships. And we have come up with a tensor-based approach for finding these communities, and in particular to be able to incorporate mixed memberships or overlapping communities. So I'll give some details, but most of the previous guaranteed approaches have been limited to the scenario of having a single community for every node. A hard clustering problem, you want to group nodes into different clusters. But we want to think of this as a more soft clustering of now categorizing nodes into multiple different categories and how to go about doing this and what are the relevant applications. So that's kind of the overall view here. This is joint work with a number of collaborators. It started out at Microsoft Research. In particular, I worked extensively with Shyam Kakre and Daniel Shu there, who was a postdoc. Now he's at Columbia. And my students have also been since involved. They implemented these methods on GPUs and ran it on many different real data sets. So also have some very interesting empirical results as well. So I mean that's the overall view. But again, at any point, feel free to interrupt. I like to keep it interactive. Okay. So I'll just describe a few applications which I'm sure many of you are already very familiar with. A natural place to think about communities or social networks. In fact, that's where the idea came about. Even way back in the 1930s, the idea was to think about how people communicate is kind of dependent on their inherent beliefs or interests and so on. So can we model social ties through the notion of community? So this is very natural, right? You can think of them even in the context of collaborative networks and so on. And even in biological sense, this is a very natural problem. You always have like kind of common groups of say genes which are regulated by similar regulatory processes. So you can again now group genes into different communities. And currently I've started working with some neuroscientists to look at like how we can think of the connectome data, which says like how neurons synapse with one another. Like the hypothesis is that this relates to their functional capabilities. Like there's if you want to get a functional map of the brain, we can hope to do it if we had like tractable means of identifying communities from such neural interactions. Another natural setting is, of course, recommendation systems, right? These are hugely popular. Just one example that I can give here is the Yelp reviews. So users go into Yelp, they review restaurants and various other business categories. And even like you can think of a very simple question of like how likely are users to review certain businesses, right? So not even the review text, like you can even go deeper in, but at the high level, you can even ask like, why do users pick certain restaurants or certain businesses to review? Most likely they're in the same location, they have similar interests, like for instance, if it's like hobby shops or something they deeply care about, right? So there are like some users that have very special attributes that gets them interested in that particular business. So you can think of now communities of different users, which are like their attributes, and also communities of different businesses. And it's a bipartite graph from users to businesses, and how likely, like what is the distribution of this bipartite graph is dependent on their underlying attributes. And in all these instances, it's very easy to observe the graph. So you can, know how people talk to one another, or how, at least to some extent, neurons synapse with one another, and so on. But it's very difficult to measure the underlying communities in most instances, right? So that's the problem here of community detection. You'd like to learn about these hidden communities just by looking at the observed network, right? So the mathematical problem is you have a random graph, a realization from a random graph, and because we have we also are, say, aware of some of the probabilistic model behind that, and using that, we'd like to learn the underlying communities, right? So that's the problem. And I talked about probabilistic models, and I emphasized conditional independence. So what is the basic intuition of using conditional independence here? So it's like asking like how informative is the graph about the underlying communities, right? And in the simplest of the setting, you can think about like this being highly informative. So the idea is that like all the correlations between different edges can be explained due to the communities. So it's almost like the graph exists because of the communities, right? So this is the main intuition that let's have conditional independence of all the edges given the community memberships. And the classical model that exploits this is this popularly known as a stochastic block model. So here every node belongs to some single community, and the probability of two nodes connecting with one another is only dependent on the community memberships, right? Once I tell you the memberships of all the different nodes, there's no other dependence between the edges. So you can just kind of think about this like a graph representation, right? Like each one of this is like a community, and this particular example, there is very high probability of connecting within the network. It's almost close to 1, so it's each one of them is a clique, and there are very few edges across different cliques. So you have much sparser connectivity across different communities, and you can see that even visually that, oh, I can label this as a community, this one, and so on. Right? So it's a very simple model of thinking about communities. Right? But the main limitation, as I've been stressing from before, is that they only can incorporate nodes being in a single community. Right? In some sense, all these different clusters are completely non-overlapping, and a node strictly belongs to one of them. Whereas in all like realistic social networks, we have people belonging to multiple communities. If you think about like kind of my academic network, as I said, I was here at Cornell. I went to MIT for a postdoc. I collaborate extensively with Microsoft. So I have, in all these, I belong to all these multiple communities. You can similarly think of my research interests or various different dimensions, right? So it's much better to think about having multiple communities, but at the same time, we want some guaranteed methods. So a first question would be to ask, what are some reasonable probabilistic models to think about overlapping communities? And the next question would be the actual methods, right? Can we guarantee for these class of probabilistic models that we can recover all the communities of the nodes? Can we do it in a computationally efficient manner and in a sample efficient manner? I mean, here the sample would be the size of the graph. Because you can think of like asymptotically, maybe in a very large graph, things concentrating well, you'd like to have it in as small a graph as possible compared to the number of communities. Right? So it's always the good scenario is you have lots of nodes and very few communities. You can even see here visually that they'll be much more clustered and much easier to deal with. So these are all the questions that come up when we want to extend to having overlapping communities. And at the same time, we'd like to retain some of the nice assumptions here, especially these conditional independence assumptions. And ideally, we would like to have the stochastic block model as being the special case. Because for this model, there have been many guaranteed methods, and any method we want to extend to a more general class, right? We can then ask how well does it do in this special case. So we'd like to kind of also connect closely with this stochastic block model. And that's where, just before we get into the actual model, just you can think of like a, like how in an adjacency matrix representation, right? So this is like a simulated data. If you had like pure communities, you'd have these very tight blocks of clusters here, whereas now once you allow for mixed communities, so here the node now, instead of being like a purely one of these colors, right, that would be like these 3 communities, can now belong to multiple communities, and now you can see like the clusters are much less defined, right? There's like a kind of a lot more confusion on what's a cluster, so it should be a harder problem. So even statistically, it should be a harder problem to figure out the communities once I allow for overlap. So one relevant question to ask is, how much does the performance degrade as I allow for more overlap, right? And is there kind of a nice way for me to control this overlap in a probabilistic model? So these are some of the things we want to worry about as well. And so the mixed membership model that I'm going to consider is going to be having the stochastic block model as a special case, and still now, in the general case, it will allow now for nodes to be in multiple communities. So you can just think of a toy example, like a person having multiple interests, say in sports, in computers, in shopping, and so on. So that's what I mean by mixed members. Now for each node, you can now think of a community vector. So for each node I, let's say phi I is a k-dimensional vector where k is the number of communities. Right, and now this, I'll just think of this as like fractional memberships in different communities, right? So in like all the k communities, I just sum up the weights to 1. So this is just a reasonable assumption. And now the question is, once I have these communities, how they lead to edges, right? Like kind of maybe say, think of like these two people connect because they have common interests in sports, but they only spend part of this time in sports, and similarly say for this person and so on, right? So how to incorporate for the fact that they're not completely in the community, but only fractionally there. And so for that, we can think of a model that's kind of a linear combination of the probabilities if they were pure, right, weighted by the amount that they spend in the communities. And between different edges, we'll still retain the conditional independence. And in fact, this will be crucial for the tensor forms that I'll present. So the idea is that we still have conditional independence of all the edges given the community memberships and the nodes. But now for the probability of, say, an edge between nodes I and j, once I condition on those two communities, right, is a linear combination of the probabilities, as if they were pure. So this matrix P here is a k by k matrix of like how if there were pure communities, there are certain probabilities of connection. And now I'm just weighting them by like the amount of time the nodes spend in those respective communities. And so this is the model. It's, like as you can see, it retains a lot of nice properties of the stochastic block model, and kind of the only extension is to now allow for nodes to be in multiple communities, right? But still not, this is not very specific, because what I'm missing is that I'm allowing for just any general notions of mixed membership, right? So now we can't expect to have identifiability because I can just call this a community or this a community, right? Like so you could think of having multiple ones. So what we'll do now is also fix the distribution for how these node memberships are done, but still something that's reasonable. So if you think of any real-world network, right? So as I said, limiting the node to have a single community membership is bad, but still it's not realistic to think of nodes being in all possible communities. Like if you think of my research interests, like they don't span every possible, research interest that's out there, right? So it's still reasonable to think of a prior that encourages sparsity in these community memberships. And one such model is the Dirichlet one. So this model was earlier introduced. In fact, it drew inspiration from this popular LDA model or the latent Dirichlet allocation for topic modeling, and kind of this was a community version of it. And here the assumption is now all these community membership vectors spies are drawn from a Dirichlet distribution. So if you think about like what this Dirichlet distribution means, right? It's a product form and it's weighted by these kind of parameters alpha j's. This is known as the concentration parameter. So here the intuition is, let's take the extreme case of sending these parameters to 0. If I take this limit, what happens to the distribution? So in general, the distribution is on the simplex, right? Because I have the constraint that across the membership across different coordinates should sum to 1. So any point from this distribution is on the simplex, right? The k-1 dimensional simplex. And in the extreme case, when I send this concentration parameter to 0, you have this degenerate distribution just on the vertices. So there's only probability mass on the vertices and not anywhere else on the simplex, right? So what is this model? Right, so what happens? Like the pi i's can be only one of the vertices, right? So what is it? It's that's a basis vector, right? So it's only one on one of the coordinates, right? So we are back to the stochastic block model, right? Because then there's conditional independence. It only depends on the community that the node belongs to. So you can see that in the extreme case, we do have a stochastic block model. But now, as I allow for some non-zero alpha j's, I can now have these vectors to be drawn anywhere else from the simplex as well. But the probability mass of where the vectors are drawn from will depend on the amount of concentration. So essentially, as you keep increasing this concentration parameter, there's more probability mass flowing towards the center of the simplex. So if you take the other extreme of sending this to infinity, you have a degenerate distribution at the center of the simplex, right? So this is the vector of like all 1 over k, right? So it's like I have equal amount of time in every possible community. And sure, this is unrealistic for most of the real world scenarios, but you can see that I expand the entire range. I go from like just being one community to being all communities. And the intuition is, that's why it's called a concentration parameter, because the probability mass concentrates more as I keep increasing this. And what we'd like to ask is how can the method incorporate this amount of concentration or the amount of overlap between the communities. So I'm just going to take like the overall concentration along different dimensions, so call this alpha 0. And you can argue that for this, under this probabilistic model, roughly the amount of sparsity you see, or the number of non-zero entries in this phi vector, which would be kind of the number of communities that a person belongs to, is like order alpha naught with high probability. So this concentration parameter denotes like the extent of like non-zero entries that a community vector is supported in. Right, so like kind of how much you expect the different communities to overlap. Yeah.
So in certain cases you can expect certain pairs of communities to have overlap while other pairs.
Absolutely.
How does that model?
Yeah, so because this, we are only looking at the total amount.
Yeah, but
so
here the parameters are one for every community, right?
They're not. I mean, that's just the overall thing. That's just the, because I think of it as a fractional membership, right? But the individual alpha j's can be different. So if one of the alpha j is much larger than the other, that'll lead to a larger community, right? So because I'm only controlling for the total amount, I'm saying kind of roughly overall there is like some amount of number of memberships that a node can expect, but like how likely a node is to be expected to be one particular community will depend on the individual alpha j's. So I'm not controlling those.
If I understood Ashwin's question, I think maybe he was saying that membership in certain communities could be expected to co-occur more frequently than membership in other community pairs.
I see, so the
So
correlation.
yeah,
you're absolutely
the
right.
pi variables being independent, subject to normalization.
Yeah, that's a limiting
is,
factor. Yes, I agree. The correlation is definitely constrained by the Dirichlet one, but you can allow for different sizes. That's like kind of saying the individual alpha j's can be different. And yes, that is the limitation of the Dirichlet model in particular also, and not just that part, but the part that we also assume this linear combination also rules out certain kinds of models. For instance, like enemy ties, like just because this person is in one community, I completely rule out any connection with this person, right? So because I'm taking the average. So yes, there are limitations in this model, and but the question is kind of having a combination of both, like a reasonable model as well as a guaranteed method, right? So there are definitely other options to do that. Yeah. Okay. So this is the, so the overall model description is that we are drawing these community memberships from the Dirichlet prior, and then assuming that the probability of connection is a linear combination of like their, if they were pure communities. And the sparsity can be controlled by the amount of concentration for the Dirichlet distribution. And so that's kind of the main argument for using this Dirichlet-based community model. And now, of course, there are the challenges of like, is this model identifiable, right? If I assume like this Dirichlet prior and I observe the graph, can I actually hope to recover the communities? And now we're going to use a moment-based approach. And then the question is, what order of moments is needed for identifiability? And then, of course, in practice, you only have samples. So what are the perturbation guarantees? And what are the actual methods to guarantee learning? So these are all the questions. So this is the overview of the approach. As I said, we'll think of it as a moment-based approach. I mean, this is very classical to ask, there's been the Pronis method, then the crosslink for a long time. Pearson even goes way back into like late 1890s and so on. And the idea is that I have the moments from the distribution, I want to invert them and get the parameters. And the notion of a spectral approach to solving these set of equations is to be able to reduce these equations to solving a spectrum of a certain matrix, right? These are all kind of non-convex approaches in the sense like, it's computing eigen system or SVD, but they're still computationally tractable. So you can still guarantee, that these approaches will succeed under some set of conditions, but they're not convex. Right? So typically many of the guaranteed methods are convex, so I just want to emphasize that. And with respect to this particular problem, we want to think of here the distribution is one of the random graph, right? So I have a random graph distribution, and I observe the realization from it. And now the moments here is kind of much trickier, because you can think of the moments as like different forms of subgraph. Like you count different subgraphs in the overall graph, like say the number of triangles, number of stars, and so on. So it's kind of also combinatorial in kind of what you choose to count. So you can get all these different kind of moments. And now the question is how to incorporate them to obtain the parameters. So the parameters for our model are all these community membership vectors, as well as this what I call like a pure connectivity matrix, right? Like if there were pure communities, there's some probability of connectivity. So I'd like to recover both of these.
What do you observe?
The graph.
I see.
So it's a realization from this distribution, right? So it's a large graph, and you have all these homogeneity assumptions. So that's why you can hope to recover these parameters, right? So and then after that we'll see that in fact this reduces to solving a tensor eigenvalue problem, and we'll show that it's also tractable. You can kind of do the notion of a tensor power method, which is kind of an extension of the matrix power method. And finally, hopefully I'll have time to describe some of the implementation details. Like we implemented it on GPUs, made it scalable, did some careful parallelization, and it runs very fast.
Are you treating K itself as a late variable?
So for now, let's assume fixed. Like in practice, we can cross-validate, and you'll see like in kind of the first step is finding the SVD of K rank SVD. So you could even like choose K depending on like how, what's the decay of the singular values. So yeah, we can go beyond that. But just for this talk, let's assume it's fixed. So this is the overall approach. So what I'll do first is to just give a, yeah.
So if you draw different realizations, do they all show up the same number of nodes, or sometimes?
No, just one realization, right? You have a large graph.
I know.
It's
yeah,
just
but in terms of described by the distribution population, right? So do you always see n nodes in them?
Yeah, just n node. It's n fixed nodes. You see a graph, and you see the whole graph. Yeah.
You could do give sampling for this too, yeah?
Right,
That's
but
just
like
the approach that you're going to.
And like how long it mixes, in general it should be exponential time. So that's the popular approach before this has been the variational approach. You do variational relaxation, you run this, and we'll compare with that in the prior empirical results. Okay, I mean this is much faster. With all the parallelization and being on GPUs, there's just like more than orders of magnitude difference in running time. Okay, so we'll come to all that hopefully. Yeah, so first I'll not describe the method. So I'll describe the method later on, but for our method I'll describe what we can guarantee, right? So as I said before, the main the things we need to make sure are there are enough number of samples, right? So the intuition is like unless I see a large enough graph compared to the number of communities, I shouldn't be able to recover. And in fact, this is related even to the planted clique problem. There are known computational lower bounds saying that you can't do better than like square root n sized cliques, right? So you can't detect smaller ones with computational tractability. And we'll see that, in fact, we are tied up to that bound as well. So that's one parameter to control, asking how many samples we need compared to the number of communities, right? So that, let me call that n, and k n is the number of nodes. And let me take just a special example of the connectivities. Let me just say like the probability of connection within a single community is little p, and if you want to connect two different communities, it's q. So this is just convenient to describe the results. The general ones are in the paper, and the theoretical results appeared in the court this year, the Conference on Learning Theory. And so now the question is a statistical one. So even if you recall the earlier figure that I had given, it was all these clusters, they were tightly connected and very few edges here, right? So you do need to see like a difference in like P versus Q, right? You need a good separation between the two only then you can hope to identify. And in fact, this is a statistical question. If this difference is smaller than some amount, you should not be able to distinguish two communities, right? So if there are like lots of edges here as well as between them, there's no difference, telling that they are two different communities. So there's even a lower bound for that, and we'll see that ours is tight up to polylog factors even in that. Right, so that's kind of the overall result that, first of all, ours is the first guaranteed method for learning probabilistic overlapping community models. So I don't have time to go into all the related work, but all the previous ones have been like more kind of combinatorial conditions on what overlap means, and the methods are also very combinatorial. So ours is kind of for a probabilistic model, and what we go about is like showing it through a moment-based approach. So as I said, the very first thing then would be to establish correctness. So if I gave you the exact moments, that is I gave you the expected forms, I should be able to exactly recover all the parameters. And then of course the question is with samples, how well can I do? Right, and these are the sampling requirements. So as I told you before, let's first think of alpha naught to be 0, which is the special case of the stochastic block model. Then the number of samples should scale as square of the number of communities. Just for simplicity here, I've just shown them to be the uniform community case. So all the communities have size n by k. Right? So then this is nothing but the square root n bound, right? The size of each community should be like of the order square root n up to polylog factors. So it is tied up to that bound for the stochastic block model. And the other is the separation condition. So the separation of like being connected within a community versus between two different communities is large enough. And this turns out to be also, for the stochastic block model, also the lower bound for statistical identifiability up to polylog factors. So we are tight guarantees for the stochastic block model for our method. And now you can see that we also have the guarantees beyond the block model. Now I can allow for a non-trivial overlap between the communities, and it's a very weak dependence, right? So it's saying like this alpha node, you can think of it as like the amount of membership, like the number of communities that a node is part of on average. And so it's just like the square of that amount. And in the realistic scenarios we talked about where, say, this alpha node is a constant, so every node is part of only a constant number of communities compared to the overall. In fact, there's no performance degradation in the order, right? So this is, and then it's only quadratic. So what we have is, the tight performance to the stochastic block model. So it's kind of, doing as well as any of the state-of-the-art methods for the special case. And now we are able to extend it to this more general class of models that allows for overlap. Right, so this is the overall set of results, and now what it means to be even correctly recovering the communities, right? In the stochastic block model, it was clear because I only was like, either I was correct or I wasn't, right? It's just a 0-1 thing. But now I have all these real numbers to compute, and so with samples, indeed, I would have perturbations. So what we can think of then asking is kind of like a norm guarantee. So we can, for instance, we give like L1 norm guarantees on how well we can estimate the community memberships of all the vectors over different communities. And you can also ask about how well I can estimate the parameters of connectivity across different communities. I mean, the details are in the paper, but these are kind of, when we mean by recovery, we mean like kind of these norm guarantees on what we estimate. But you can also, convert them to like support recovery guarantees. So in most, real applications, you may be interested in asking what are significant communities for this person, and what are also the communities for this person where I'm sure, this person does not belong to. And we can provide like zero error support recovery guarantees with high probability in that scenario. So this is just saying that if for, say, all communities I and all nodes j, if, say, this particular weight was large enough, then my estimator will give it as 1. And if the weight is small enough, my estimator will give it as 0. So there's some intermediate scenarios where we may not be so sure, so we can't cover the whole range. But like for large values and small values in the community weights, we are able to correctly classify them into like 1 or 0. And so we can also convert like some of our norm guarantees to also like a notion of being able to list significant memberships for every node in the network. So these are the flavor of guarantees, I want to spend some time on the algorithm. Any questions here? So let me now show you the actual method that achieves these guarantees. So as I said before, the main idea is from the graph, I want to mine different kinds of subgraphs and then compute like how likely they are to occur, right? Like the counts of them, and then use that as a way to learning the parameters. So you can think of different possibilities. We'll just limit to this object 3 star. So it's a star with 3 leaves, and we'll count them across some fixed partitions. And the reason why it's 3 star is that this is the minimum required. In fact, you can show that if it's only a 2 star, it's not enough for identifiability. So there could be multiple models that explain the same thing. And if it's more than 3, of course, it's okay, but it's not okay in terms of samples, right? It's a higher order moment, so you would need more samples to compute. So you don't want to go to a higher order moment unless you have identifiability issues. So, and that's why we'll limit to this 3 star object. And even further, we'll partition it so that every node in the star is in a different set. Again, this will remove some of the dependence issues and makes it much more convenient to apply conditional independence relationships. So the exact object I'm going to do is look at every triplet here. So take a node from each of these sets A, B, and C, and ask how many common neighbors does it have in this 4th set X. Right, so that's exactly this object, right? I want all these edges, so G is my adjacency matrix, so I want all these edges GXA, GXB, GXC to be present, right? Only then this object is true. And I want to count how many such nodes are there, that's exactly this object, right, up to this normalization. And now I can think of this as a 3rd order tensor. I mean, in fact, it's a 3-dimensional array because I'm counting over all the triplets in these sets. Yeah?
You only care about X now, or do you require that A, B, B, C, A, C are not?
They're all disjoint.
So but A and B, like little a and little b, are they allowed to have an edge between each other, or?
They can, but I don't count for them. So I'm only gonna look at like these cross edges, right? And that's what is kind of needed for finding some of the communities. So you could reverse the roles and kind of find for the others. But for now, let's just limit to these edges. Okay, so, and now writing it like in terms of like the outer product of the neighborhood vectors, it's this form, right? So for those who are familiar with the outer product notation, these two are exactly equivalent. So if this is a 3rd order tensor, if I wanted a particular entry in this of say corresponding to little a, little b, little c, that's given by this form, right? So these are 2 equivalent representations. So you can see here that this tensor is formed as an outer product of like neighborhood vectors of each node X to each of these sets, right? So I have like kind of these 3 neighborhood vectors going out for every node X, and I'm taking the average. And this will be my object. I'm going to ask like how in expectation it looks and how it corresponds to a particular tensor form, which we'll argue is amenable for decomposition. It will turn out to be a low-rank tensor, and we can apply efficient techniques to do the decomposition. And in fact, in practice, we'll be never actually forming this tensor, right? Because this is actually given by like the outer product of the neighborhood vectors, which I have access to. And I don't want to form a large tensor because this is an n-cube object. So just to keep in mind that first, just think of like intuitively how I can manipulate it, but when I run it as a method, it will not be kind of forming this tensor. Right, so now the question is, first I want to look at the exact moment. So if I take the expectation, what form does this 3 star object have, and how I can argue for identifiability, like how I can establish that this has all the relevant parameters that I'm interested in, right, that I can uniquely recover. And so let me just do it for the stochastic block model because it's easy to argue for the expressions. And for the more general Dirichlet form, there needs to be some moment corrections based on the Dirichlet moment forms. So the expressions are a bit more involved, but the intuitions are very similar. So the first idea is to think of this as, if I just look at like a neighborhood vector, right? So I want to ask like from the say every node little x here, how I can obtain a neighborhood vector to this entire set A. So that's exactly this vector here, gx, like capital A. Right, so in expected form, how does this look like? You can write it as a linear map of the community membership vector of X. And so this is the main intuition that this is essentially a linear model. right? So I have this hidden, I want to again think of this as a latent variable model. So this pi x is hidden, and the how it associates with my observed variable, which is the neighborhood vector, is a linear map, right? So this is just for like going to a single set. Now I have this 3-star object, so I have simultaneously neighborhood vectors going into these 3 different sets, right? And I have the same form of the, I have like a fixed membership vector here for x. And that you can show is in fact like a multilinear form. So it's like kind of, this is where the conditional independence relationship is crucial, because these 3 edges are conditionally independent once I condition on what the membership of node x is. So this is what I also think of it in terms of mixture modeling as a multi-view model. Like I fix the same latent variable and I take multiple independent views of the model. And in fact, that's what inspired us to think of this kind of a partitioning and come up with this model. Like we earlier started out with doing mixture models and coming up with such third-order moments. And so the main intuition here, this multi-linear form, critically depends on this conditional independence relationship. Right? So this is kind of the main, I would say, geometric picture to keep in mind. First, I'm going to select a latent state. So in this case, it would be like one of the vertices on the simplex, because it's the stochastic block model. So every node x here would select one such vector, right? And in expectation, if I want to ask like what these neighborhood vectors look like, they're exactly linear maps of this, right? Individually, they're linear maps. And if I look at the overall 3-star object, it's a multilinear form that has, along each of the modes, these same linear maps, right? FA, FB, FC are my matrices corresponding to linear maps into each of these sets individually, and the 3-star object kind of combines them together. And for those who are aware of the tensor forms, this is exactly like a CP form or a Kanekov parafact form. So in that form, you can see here the number of terms is k, where k is the number of communities, and each is a rank 1 tensor. And so you have kind of all these factors, right, corresponding to the 3 modes here. So each one of this is a mode, and I have a rank k tensor when I have the expected 3-star moment. And this is, I would say, a critical observation that even though the ambient dimensional tensor is huge, right, it's n cube parameters, but the number of free parameters is much smaller. It's only a rank k tensor. And now, all the machinery goes into asking how I can do this decomposition efficiently. Because the main idea is that these, matrices FA, FB, FC contain all the information about the communities. So once I can recover these parameters, I can do some just linear transformations and also recover the communities. So the main machinery now reduces to finding a low-rank tensor decomposition of this 3-star object. Okay, so now I'll spend some time talking about what are some tractable means to do tensor decomposition. So as I said before, we are never forming this huge tensor object, right? So we want to implicitly manipulate it, and we want to do it in a parallelized manner. And it should also be robust, because we don't have exactly a rank k tensor. There is some noise because we are estimating it from samples. So these are all the things we'd like to keep in mind. Right, so this is like kind of a picture that I always like to think of tensors. Like for 3 dimensions, you can still represent them as a box. So I will stick to 3-dimensional tensor. And the idea is like this overall tensor can be decomposed into k terms, where each term is a rank 1 object. Right, and the notion of rank 1 tensor is kind of extension of the matrix rank 1. In matrix, there are only like 2 vectors, u and v. You can think of them as autoproduct of them. Right now, there are 3 of them, and so on. And you can see that's exactly what each of the terms are, and you have some k of them. And as I said before, our running assumption is that the number of communities is much smaller than the number of nodes, right? And in any realistic setting, like even if the graph is say millions of nodes, it's like very rare to find like more than say tens of thousands of communities, right? It's like so there's a huge gap between the two, and we'd like to exploit that fact to ask how I can do low-rank tensor decomposition efficiently. And for those who are aware of like some of the techniques to do low-rank matrix approximation, right? In a fast, scalable manner through randomized methods. Like, you can always run SVD, but SVD is expensive. In the worst case, it's like in cube, right? So you want to come up with other faster means to do using the fact that it's a low rank matrix. And so there have been all these random projection and like more sophisticated ideas where the idea is to first reduce the dimension of the matrix in that scenario, and then do exact SVD on a smaller one. And we'll also exploit a similar intuition, but for tensors here. So because we know that it's a low rank tensor, the number of free parameters is much smaller than the size of this big tensor. So we won't attempt to directly decompose the big tensor, but reduce dimensions, so convert it to a smaller tensor, I'll call this tensor T, and then attempt to do a more careful decomposition of that tensor. Right? So the very first step is reducing dimension. This has like a lot of advantages, right? Because tensor decomposition can be expensive, but now I'm doing it on a much smaller tensor. And also it's potentially better for noise because I'm trying to kind of find a decomposition in a much smaller dimensional space. So this is the kind of the very first step of thinking about reducing dimension, and we'll use again a notion of multilinear transform to reduce dimension. So essentially, think of it as I'm reducing dimensions along each of the modes of the tensor. Okay, and so here there are some details that I won't be able to get into, but the main intuition is I had these factor matrices along each of the modes. So that was this matrix FA. Think of these like as like kind of the set of columns, right? Like which directions they point here, there's FT and FC. And in general, they are not orthogonal, right? So here you see the first difference between a matrix and a tensor. In the matrix case, if I had a decomposition that was not orthogonal, it's not unique, right? Unless you put some other constraints, there's no unique decomposition. Whereas in the tensor, it's still possible to get a unique decomposition even when the factors are not orthogonal, right? But for us, it's always more convenient to think of it as converting it to a form that's orthogonal and converting it back. So what we'll do is, as we are doing this dimensionality reduction and reducing it to a smaller tensor, we'll also reduce it to a tensor of a tractable form. So meaning that the earlier form did not have an orthogonal decomposition, we'll also convert it to a form that is orthogonal components. So think of it as like after transformation, have this tensor T, which is a k by k tensor, and all its different rank 1 components are orthogonal to one another. And I can achieve this because I have kind of access to like the span of these matrices. I can either do like the neighborhood or like pairs. There are different statistics I can incorporate and come up with what exactly this transformation should be. And as I'm doing it, I'm also going to symmetrize and come up with a tensor that's symmetric along each of the modes. So here you see each component is the autoproduct of the same vector rather than 3 different vectors. And this, I would say, is kind of making the tensor decomposition problem much easier. Not only is it on a smaller tensor, but also it's a much better structured tensor. Right, and this is kind of standard as it's known as whitening in ICA and related literature. So this is something that people do a lot. Okay, so this is the first step of doing dimensionality reduction. The next question is, now that I have a tensor that's orthogonal and symmetric, what are some simple ways to think about decomposing it? Right, so here we'll use the notion of tensor eigenvalues. So what you can think of is what you can establish is all these components are eigendirections. So there are directions where they're pointy and have good fixed point property. So the notion of a matrix eigenvalue problem is you here in this case, there you would hit the matrix with this vector and you get back the vector, right? The direction doesn't change. And the only difference here is it's a nonlinear problem. So for third order, you can think of it as a quadratic operator. So I'm projecting 2 of the modes along a particular vector. Say here Ri is one of the components, right? So that's exactly this form, right? I take inner product here with all the directions, and because of orthogonality, the only one that survives is the one you started with. So what you can establish is that all the components of this orthogonal tensor decomposition are eigenvectors. And a very naive thing to do immediately is to think of a power method, right, or a fixed point iteration. So essentially, I start with some random direction, I keep doing this iteration, hope it converges, and it converges to one of these points. I mean, there are all these nuances, and then you can kind of make it into a method of doing it serially by deflating and trying other directions. So this is the naive method, but even theoretically, the tensor eigenvalue problem is more nuanced. So I won't get into the details. Depending on the initialization, it can go to different eigenvectors. In the matrix case, it always goes to the dominant one once you start with a direction that has some component there. But in the tensor case, that's not the scenario. But what we can show is in the orthogonal setting, the only stable points are still only these components. So we won't, with probability 1, we won't run into spurious ones and so on. So I mean, that's kind of the theory, but also in practice, right, this is kind of not, can do a lot more improvements. And that's kind of the approach. What we take is to do stochastic gradient. I mean, you can think of like finding these tensor eigenvectors as a norm maximization problem. It's kind of maximizing the tensor norm. And now, and this kind of the 3-star object is kind of formed from like the samples, right? You're kind of taking the average of the outer product of neighborhood vectors over all these samples. So you can kind of touch each sample, make an update according to the stochastic gradient, go to the next one, and so on. And that's how we actually implement this. And this is where there is a lot of room for improvement. Like on the GPU, we can limit like the amount of communication, do these manipulations in a highly parallel and efficient manner. And so there are a lot of implementation details as well here that leads us to also getting a very good running time in this setting. But like the overall, I would like say notion of what this community detection approach is doing is to first implicitly form a tensor that counts like these 3 stars, right? So it's like kind of taking a triplet of nodes and it's finding common neighbors, like asking how many common neighbors they share. And then it's finding a low rank decomposition of this tensor, and that's kind of 2 steps. One is dimensionality reduction. Essentially think of them as a series of SVD operations to now come up with a smaller tensor, and then doing a tensor eigenvalue decomposition problem to find the actual components. And then the post-processing is just kind of reversing these linear transformations.
So if I understand your method, you have an underlying probability distribution.
Yeah.
Is it hard to find the probabilities of certain structures like triangles or compute the probability under those distributions?
Yeah, so that's a very good question. So for triangles, there are a lot more dependencies, right? So under expectation, the tensor form is messier. I'm sure there are like some other manipulations you can do and try to get it to a form, but this one is convenient.
So if I understand it correctly, suppose I can compute probabilities of certain structure, and if I simply do maximum likelihood, is it similar to
So the maximum likelihood is hard, right? Like trying, getting to the global optimum. That's the computational tractability question, right? And that's why these are tractable ones. But these are not likelihood because they're not trying to maximize for the likelihood. They're kind of maximizing the norm of these tensors, which is a different objective, but that you're guaranteed that all the stable optima points are the ones of interest. So there are no spurious optima that you run into.
So if you do something like likelihood and coordinate descent, does it work, or does it like?
I mean, so that's exactly the variational approach where you do a variational relaxation for the likelihood to make it tractable. And so that's what we'll compare against, and there is, and that's been the state of art till now, right? And that's the, so this is an alternative approach. Okay, so now I'll very quickly, in the last few minutes, just go to the GPU implementation results. So I won't give the details of the implementation. So there's a separate implementation paper that's on archive, also on my website, so you can see all the details. But let me show you a flavor of results. So we looked at the Facebook data set with about 20,000 nodes. There's a data set about 40,000 nodes. So out of them, I think 10,000 are the businesses, the rest are users. And DBLP, we looked at like a subsample data of like about 120,000 nodes. And so this is like a variational method. It's variational, and then it's ours. And you can set like this k hat as the number of communities you choose. And also, like, I'd like to, especially for those who work on community detection, when I say error, right, it's very not clear what it is, because people evaluate communities in all possible different ways, and that itself is what the Wild West area, according to me. And especially, I would say, with overlapping communities, some of the measures are clearly ill-suited. Like if you want to ask, like, what is the extent of clustering, right? That's not necessarily something we want to optimize for, because when now you have overlaps, there may not be very tight connections within a community. So we'd like to kind of ignore those kind of measures. So there's been like a notion of normalized mutual information that initially was stated for the stochastic block model setting, which was exactly that, like an information theoretic setting. But its extension to, again, overlapping models is highly questionable because it's no longer information theoretically correct. So people have come up with these different scores, and we have a detailed discussion arguing like why some of them are actually flawed. So we come up with a new score where, because this is an unsupervised method, I just have like a bunch of communities that the algorithm spits out, and I have some ground truth communities. So how do I even relate with one another is the first question, right? So what we first do is like a multiple testing problem, like ask, oh, is this estimated community having good positive correlation with this ground truth community? Like, I can test for like right-sided p-values and come up with all statistically significant pairs. And then what we'll do is we'll penalize the error over all the, like how the weight is predicted across all estimated as well as ground truth ones. So in some sense, I'm also, like in the perfect scenario, there'd be like a one-to-one correspondence, right? Like the estimated community would only correspond to one ground truth community, and then I look at only the error between that pair and so on. So now I'm also penalizing for the fact that because there's overlap, an estimated community can correspond to multiple ground truth communities, and I want to penalize for the case when I have these multiple matches instead of one-to-one.
So is your K calibrated to the number of ground truth communities?
Not in this case, right? It's like we could fix it to some K hat, but we can make it to be the same as well. So because we kind of are,
Are they at least within an order of magnitude of each other?
right? So here, like, yeah, they're very close, right? 360.
Ah, so the one in parentheses.
Yeah. This is the true one, and this
Okay.
is like what we
Okay.
see. And because I guess we also wanted to kind of get a sense of running time, also, like, so we tried out different K hats, and but yeah, even better, you would select the same K, but you don't need in this framework because we are kind of also allowing for penalty if there are multiple ones. And yeah, so here, now there's also the notion of recovery ratio, but because you can like post-process and zero out many of the smaller entries. So how you threshold would also determine what communities you find. So if you choose a very large threshold, you would only then get large communities, right? If the smaller ones may just be like zeroing out and not being recovered. So, and that's something, so it's like, here for our case, I'm only showing you a single point. So you can come up with a whole the plot of like how the error changes as you change the threshold and how the recovery ratio also changes, right? So you would get like a higher recovery ratio but a worse error in general, right? So there's a trade-off. And so what we have is like, of course, in terms of running time, there is no competition with the variational one, right? I mean, one thing though, we do run on GPUs while there's a CPU-based code. But these matrix computations are much more natural for GPU rather than a variational implementation. But even accounting for that, there is a very big difference, especially as you go to a larger data set. Like this was about 5 or 6 days, and this was like about 2.5 hours. So there is a huge difference in time. And you can also see the error, like we are doing better, we are able to recover. I think this is just like one data point, like we get like slightly worse error with higher recovery. So we can, so we're able to have fast algorithm with as well as good error and recovery ratios. When there's ground truth available, we've been able to validate that.
I was just wondering how much you would attribute running on a GPU versus using stochastic gradient as the...
So by the way, even this variational code is doing stochastic gradients, yeah. And also there's some link sampling, and this is the latest one, like, Gopal and David Mimno, who's, I don't see him here today, but, so they've had the last year's NIPS paper, and they even have the latest one where they do further optimizations. So this is highly optimized code that we took from them and ran on the same machine. Yeah, so you can see that, come up with a method that has good theoretical guarantees, but also in practice seems to be working very well. So you can also now ask for like further interpretations, right? I get all these different communities. What can I think of some interpretations? So with the ELP data set, like, so by the way, for ELP, we also give weighted edges. So the edges were the review stars. So you expect like kind of the weight also to now tell you about the popularity of a business in the category, right? And that's kind of like here we showed like the top 5 categories. So the communities that were like recovered with the lowest error, as well as the nodes that had the largest weight in them. So you can, as you can expect, like there are restaurants as big categories because everyone goes to ELP to review restaurants. And these have like kind of, and we also looked at the average star of all the restaurants in that community, and this is pretty high compared to the average, which you expect. But what is perhaps a bit more surprising is to think of hobby shops, right? When you think of ELP, it's like where did hobby shops come along, or mass media? And you can see like the number of review counts is also much smaller. So there are very few people reviewing these. But I think of these as niche communities. So these are like very dedicated users who mostly log in. They just want to review this. They don't worry about reviewing anything else. So you're able to pick out them as like separate communities. So that's something interesting we found, that it's not just the size of the communities, but how much it overlaps with the other ones. So if you have like kind of their own dedicated set of users, you'll be able to pick them up. And the other is, because we are doing all these overlapping communities, what does it give us? Right, so here, these were all the different business attributes. So because we have now multiple communities for a node, you can ask what they correspond to. And so this is the notion of bridgeness that's been used before. It's essentially some kind of norm distance from like this kind of all ones vector. So it's like how far away it's been from fully dense. And I think there's some degree correction as well, I forget the details. But here, if you look at what are the top 5 nodes in the ELP dataset, which are in the business side, you can see that all kinds of different attributes are picked up. In fact, some of them are even hierarchical. There's restaurants, within that there's American, there's like Mediterranean, right? And there's also like nightlife or pubs, and there's location. So all different kinds of attributes you can pick out by incorporating this overlapping model. Right, so this is like, whereas if it were a single community, this would not be possible, right? So you can think of this as now, even incorporating some kind of hierarchy through by allowing for these overlaps. Right, although we don't output as a hierarchical model. I mean, that's another project I've been working on, but yeah, so this is kind of the overall, so very briefly, I wanted to, here, this was just like kind of taking like, these were female and male users, somehow the text disappeared for some reason. And these were nail salons. So kind of arguing like, also like how users are discriminative in reviewing particular businesses. And guess what, this is for men. What do men tend to review a lot more than women? Tire shops. I don't know why. And just wanted to, so this is the ground truth. I wanted to kind of give you a sense, like you can also discover user attributes. And in this data set, there was only the name, and we kind of inferred the gender. So this is like our inferred genders now on the user side. And you can see like it's quite good for females, but for men, it's a lot more noisy. So it's also like kind of an art, although we don't have the ground truth, but we can argue like, that you can also recover some of the user attributes and hopefully use it for recommending and predicting.
How many users did you find who reviewed at least one nail salon and at least one tire shop?
So you can see that here. It's like there are quite a few women who do that, but there's like, there are men who visit nail salons as well. And by the way, this is Arizona, so that may also explain the preference to nail salons for men. So you can draw your own inferences. Yeah, so this is more to kind of make the point that we only showed on the business side, but you can also think about attributes on the user side to recover. Right, so that's kind of the overall idea here, like how we can think of a model where nodes can belong to multiple communities. So we came up with this probabilistic notion incorporating the Dirichlet prior for encouraging sparse community memberships. And we use the approach of moments and to think of these 3-star count objects as my object of interest and argue that under exact moments this has the right amount of observations to recover the parameters, and you can reduce it to a low rank tensor decomposition. And you can do this very efficiently as well. Yeah.
So you just use the 3-star counts, but is it possible to use other counts and that boost the performance?
Yeah, so that's the comment I made before, right? So typically you don't want to go to high order moments because you need more samples, right? And even in practice, this won't be not
3-star count
really
is like
robust.
just a graph structure.
Yeah.
You also have counts for triangles and maybe other
Yeah,
numbers.
and so for triangles, as I made the note earlier, there are a lot more dependencies. So if you just wrote the raw moment, it's messy. I mean, there could be other manipulations that's possible there. And so, I mean, the thing is there aren't that many objects for like small number of nodes, right? So, and you don't want to go to higher order unless, you believe that the number of communities is really large, right? In that kind of setting, you could then, like more like a hypergraph model would be pertinent, but at least in all these data sets, it's like pairwise relationships is more than useful. So the question is really an application, you can easily extend to like a more hypergraph setting or think of like a larger subgraphs, but where, where are there really that many communities and what data set is it applicable is something that I at least haven't come up with. Maybe more in image applications, I would think, but that involves this whole sort of initial pre-processing and kind of whole set of different challenges.
So I'm curious about the normalization and the base shape higher. So say my graph has a few lonely nodes who aren't part of any communities.
That's fine. You can make it a gen community, right? You can.
Right.
Yeah.
So is it like trivially extensible by just modifying the k hat? But then it feels like I need to put in like a mutual exclusion constraint to ensure that no other node gets assigned to this community or something.
I mean, there may be some amount of noise, right? If like it's like, and then you zero out on the threshold.
Okay, so that's the recovery rate that you were talking
Yeah.
about.
Let's thank Anima again.
Thank you.